Commit to memory. Which of these prefixes did I say you need to know?
Kilo, centi, milli.
Kilo, centi, milli. Yep, and one more.
What?
Micro. Great. I got out my little. Okay, yep, you got it. So kilo, centi, milli, and micro. Yep, yep. And usually I don't circle them, I put like a little arrow. So we also did this slide, and we kind of came to see these blue boxes. They both mean the same thing with regard to the relationship between centimeters, cute little centimeters, and meters. This is usually how I would write it. It takes 100 cute little centimeters to make one whole meter. Okay. Alternatively, especially like on that chart we just looked at, if you find centi, its prefix means 1/100th of the base unit. So they mean the same thing. Those are equivalency statements. These are equivalency statements. I'm going to go ahead and put an arrow next to the thing to memorize. And this one you need to commit to memory. Okay, so those 4 prefixes and this one equivalence. Okay, between the English and the metric system. Of course, we're all about metric, but you know, we live in an English world. I can remember being in 5th grade and vividly my teacher telling the class that by the time you guys are old enough to pump your own gas, it won't be in gallons, gas will be in liters. It's like, oh wow, man, that's pretty cool. So learn this metric stuff. And here I am years later, right? That's okay. So this is a hairy deal, and we'll be talking about this either today or on Wednesday. The fact that some quantities are exact. Actually, if I go back to this right here, this is exact. This equality is also exact. Of course, this equality between centimeters and meters came from the metric system. And so we have an exact relationship by definition. I compare that to gallons to liters and pounds to grams. Okay? Don't have to memorize those. I will give you those equivalency statements if you need them. Or if you need them to do homework, look them up. Okay? Those are approximate. And we're going to be talking today about uncertainty and all of that. So if I pick on the first one, the way you read 1 gallon is equal to 3.785 liters is we say exactly 1 gallon is equal to approximately this quantity in liters. And what we're going to see is that actually when you report something that's approximate, something with what we call a degree of uncertainty, you're like, this last digit here, which is in the tenths, hundredths, thousandths, the thousandths place, that is, I'm going to put a question mark over there. That's actually where what we say uncertainty begins. So there's an uncertain value. The whole approximate uncertain thing probably works for you. We can say exactly 1 pound is equal to approximately 453.6 grams. Again, this digit right here, there's wiggle. When I talk about wiggle or uncertainty, that question mark, you probably maybe have learned it this way in one of your other classes. If I pick on this quantity down here, we could say that grams, that scale measuring that mass, is probably plus or minus 0.1 grams. So that's the wiggle, okay? All right. Exact relationship. Now, of course, milliliters and centimeters cubed are both metric. Okay, so this is within the metric system. Those graduated cylinders y'all have in your drawers, you have like a 10 mil, a 50 mil, and a 100 mil graduated cylinder. Okay, so if you picture the 10 mil, which is usually got about the diameter of your finger, 1 milliliter of liquid is equal to a volume of 1 centimeter cubed. I didn't bring them in here today, but remember when I brought in like Jenga, the little centimeter, 1 centimeter by 1 centimeter or 1 centimeter. Okay, 1 cubic centimeter. So arrow means you got to memorize it. These, I could put arrows next to. You're going to have to know these too, but I think you're probably pretty good with these. Grams, although the gram is not the base unit. Do you remember what the base unit in mass was? It wasn't grams, it was kilograms, exactly. Abbreviation for grams is a G, lowercase. Meters, M. Liters, capital L. Seconds, S or SEC. And meters cubed would be meters raised to the third power. Okay, so this slide just kind of says the case matters. So liters would not be a lowercase l, it would be a capital L. One of the jobs as an instructor in our different fields would be to get you ready for, to get you ready for that field. So to find your way around science, you're going to want to do this, make sure you do this right. So capitals count, don't use a period, it's tempting. You know, so I mean, there's a couple things wrong with this. You know, gram, no, okay, it's just like that, okay? Even though you might think it's supposed to be this, it's really supposed to be this. And if there's more than one, we don't use an S. Okay, so I mentioned the other day about sending a sample away for a series of tests, like if you are in a factory and you need to check for environmental parameters. You might take your water sample, I don't know if this is a good example, but take your water sample and send it to a lab, okay? And they would send you back results. And the other day I said that when the lab receives it for analysis, they're going to do their non-destructive tests first. They're going to do their physical tests first, and then they're going to do their destructive tests. My DNA is coming right along with my DNA analysis, I think I told you so. We'll see if I'm related to somebody famous. Anyway, when they send you back a report, you need to know how good the analysis was. Whether it's, you know, some analyses don't do very well. I've worked in a few different labs out there, and one of the reasons you get back results from that you requested, they don't do well, is because of the sample. So it's not your fault. One is its equipment, one is it was just a bad day. So they will tell you how accurate you can imagine your sample to be. Now, to get an accuracy, what they did was probably run some sort of standard, and they said, well, or else they did like a yearly or quarterly test on that particular analysis and said, our accuracy runs this, okay, for this test. So how close was the value we gave you, the reported value, to what it really is? The other one is precision, and precision just means if I ran it a few times, which they do in a good lab, they'll tell you what sort of scatter there were in the results that their instrument gave back. So that's kind of accuracy and precision, and it really lends itself to a dartboard like this. So if you're throwing darts, of course you're trying to get in the bullseye, right? So if you get a dart in the bullseye, that means it's accurate. I don't know if you can tell this, but there's actually a cluster, maybe 3 different darts that have been thrown and hit the bullseye. So that cluster is tight, that makes it precise, and it's in the bullseye, so that makes it accurate. Check this out. Cluster's pretty good, precision's pretty good, accuracy not so much, okay? Now granted, you know, throwing darts is obvious, you're trying to get in the center of the bullseye. It's not always obvious what your true, what the real value of a test is. Let's see about this one. What do you think? Is it very tight? Yeah. I'd say the scatters, precision's looking kind of scattered. And then to get a value that was reported, what we do is we would take those 3 values and we would take the average of those 3 values. Now, you know if they're numbers, you add them up and divide by, in this case, 3. But if they're just like visual, we would just kind of look where the middle of these are. And I'd say the middle is about right there. So our middle is not very accurate, okay? Spread, poor precision. The average, not in the bullseye, poor accuracy. That was bad. Now, I don't know, I've never seen anybody do this, but to me there's another scenario. And I'm just going to draw on my red pen. I'll make it, I'll go ahead and make it 3 darts. What if you had a dart here and you're like, dang, that one's not very accurate. I have a dart here, dang, not very accurate, big spread, poor precision. And if I had a dot here, what would the average of those 3 darts be? Yeah, in the middle. So, for what it's worth, precision for the average. So that would be good accuracy. So oftentimes when you guys do a lab experiment on Thursdays, it will tell you what calculations you need to do. And one of your calculations oftentimes is what is your error. And there's 2 ways to describe your error. One is, and I guess I'm getting a little ahead of myself. So to record your error, I'll tell you the 2 ways. And in that, to do an error, what I'm going to have to tell you in the write-up is what's the known value. Sometimes I'll say what's the textbook value of what you guys were trying to measure in the lab. At this point, I'm like, well, if you already knew what the value was, why did you make us measure in the first place? That's not the point. Okay, so error is how close or how far from the true value you got. Uncertainty then would be that wiggle. Uncertainty would be that spread. So uncertainty is actually associated with precision. And we don't do, well, I guess the first lab, you guys do like in order to understand uncertainty or to measure uncertainty, you have to do something repeated times. We don't do a lot of that in our lab, but we are for the first one, you're going to do like 10 measurements and you're going to see what that spread is. What's the uncertainty? What's the precision? This is what I started to say. So error actually can be measured in a couple of ways. There's kind of the quick and dirty absolute error. Absolute error is just what you just take the known value. See, that's right. Yeah, you take the known value, and from that you subtract your value. So known or the book value minus lab value. And if known value is in grams, and if your value obviously would be in grams, can you see where the units that you got back? This is your error. This is ABS, or absolute error. It's funny because that's absolute, and we do some of this. This is my absolute value sign in math, okay? But we're not going to do that for here because it does make a difference. Because, you know, if your bias, let's see, if your bias low from what it is, guess what? You'll get a positive absolute error. If your bias high than what it is, you'll get a negative. Okay, so the sign does make a difference. The other one is relative error, and we do a lot with that. And relative error actually takes, I don't mean to throw you off or anything. Well, okay, I'll do it this way. So for relative error, anytime you see ratio up here, hopefully you should be thinking divisor. So relative error is a little divisor or a little division problem, and basically you take the absolute error, which is your known minus your lab value, divided by your known. And times, well, I guess that would give you relative error. I usually get percent relative error, which I do one more thing. Yeah, let's do this. I'll change this to percent times 100%. So that will give you relative error. And there is a sign associated with that one too. Positive, negative. All right, people, so this one will be due when we meet again on Wednesday. Okay? So let's take a look at, it's too early to quit, even for me. All right, so let's go on to part 3. We do a lot with, let me put it this way. In chemistry, there's the numbers part of chemistry, and then there's the pretty part of chemistry. And we'll be doing a little bit of both. So we need to, understand the numbers, more things about the numbers part of chemistry. And when I say the numbers part of chemistry, this subject of significant figures, this isn't just related to chemistry. Okay, this would be all sciences. And then might I also say, because sometimes students, when I get through this part, they're like, really, does it really matter? Okay, and it does matter. This part we're going to ultimately build up to, how do you round? How do you round? How do you round your numbers? And you'd be like, and you might have learned different ways, but you're going to round your numbers according to what we talk about here. And I'm going to build up to kind of why you round that way, and whether you're convinced or not, you still have to round your way that way. Okay. So, significant figures. I kind of sometimes say, thou shalt not lie. So, like, if you write down a value of 7.35, and it's a density, grams per milliliter, you know, and the symbol for density is this Greek letter rho. Okay, so if you write down that density, you have to be relaying to the world, not just me, maybe your peers, but you have to be relating to me and the world that actually this relays this relays kind of the uncertainty associated with your mass, which is grams, and your volume, which is milliliters. How you round that, I'm going to kind of show you how you round that. So all values have wiggle in them. All values have uncertainty. All measured values, well, there are two types of measured values that don't have uncertainty, and we'll kind of show you about those. So here's the deal. If we go back to, I don't know what day, 7.35 grams per milliliter, okay? When you report that, it's kind of like I mentioned a minute ago, I'm going to put a question mark over this digit, this 5 digit in the hundredths place, because that's where you are allowed to have a little bit of wiggle. You can only have one uncertain digit. We're kind of building up to how you round, why you round. Only one uncertain digit, and it's going to be the last one, the one to the far right. Okay. So in these slides now, I don't put a question mark, but I just make it red hot. So this could be meters, this could be grams, this could be liters, but somebody has measured 4.1267. Let's go ahead and call that micrograms. The symbol for micro is this Greek letter mu g, micrograms. So somebody gave you a mass, oh my gosh, they must have had a heck of a balance. Okay, so that last digit in the tenths, hundredths, thousandths, 10,000ths place is uncertain. That's cool. You only have one. This is going to be kind of a close-up of a graduated cylinder, and you're going to be using graduated cylinders in your first lab, and it makes kind of this, water does anyway, it makes kind of this concave sort of thing at the top. And you're going to need to be able to estimate to the nearest tenth between gradations. So if we get our bearings, let's see, it looks like every gradation is 1 milliliter. Do you buy that? It's because we have 10, 15, 20, and between the 10 and 15 we have 5 gradations. This would be 10, 11, 12, 13, 14, 15. So, and it's this is not like the Mrs. Snipes made up rules, okay? We're going to have to kind of estimate. Do you see where this little meniscus, we call that the meniscus, you see where it's not on 21 and it's not on 22. Okay, so it's between 21 and 22. So the rule of thumb is going to be that you're going to give it 21 point, and then you're going to estimate. Now, what this slide's done, I don't know if you buy this, but they've gone ahead and estimated, like it looks like 6 clicks, 6 out of 10 clicks up between the 21 and the 22. So it's 21.6. Okay. One of the things about this class, and I try to, is there are no naked numbers. In lab, there are no naked numbers when you go to work problems, so it's 21.6 milliliters. Okay, so that's the estimating part. You'll get some look at that, use of that this semester. So there's uncertainty or wiggle with all measured quantities. There are 2 exceptions, and here they are. Okay, one is if you are counting. So like in here, I could count people and we're up to 7, right? We have, it's not like we have 7 plus or minus 1 person. Okay, we have, well, if you count me, we have 8. Okay, 7 students or 8 people. Okay, that's by counting. There's no uncertainty, it's exact. Now there's some awesome cool things that go along with exact numbers when you go to use exact numbers in calculations, so keep that in mind. The other one's by definition, and we've seen 2 definitions this afternoon. One definition was that there are 100 centimeters exactly in 1 meter. That's by definition within the metric system. The other one was, what's the relationship between inch and centimeters? 2.54 centimeters per inch, exactly. Yep, that's by definition, so you got it. So if here in a minute, I'm going to actually take a measured quantity and we're going to count significant figures. Sometimes I call significant figures significant digits. Significant figures, significant digits, it's the same thing. If we're looking at a number that is exact, either because it's counted or by definition, there's an infinite number of significant figures, otherwise called sig figs. Okay? So let's take a look at now numbers that aren't exact. How are we going to look at a measured quantity? And you're going to be doing this in your calculations, where there's the number part and the pretty part of chemistry. The number part of chemistry in your calculations, you have to count sig figs, especially if you're multiplying or dividing. So if the digit you're hovering over is not 0, I usually use a check mark. It's significant. So I'm going to kind of go back and forth. If you have slides here, you kind of see what I mean. I think if you go forward a slide, I'm not sure, it might look like this. So if we look at 14.32, that could be 14.32 grams, whatever you want to say. Of course, we have the uncertainty here in the hundreds place, but that's not what I'm trying to do here. If I put a check mark according to rule number 1 over all the non-zero digits, I have 4 check marks. That's it. 4 check marks, 4 sig figs. That's it. So that's rule number 1. Then I go back to this slide. This is fancy. Go back to this slide. So that's rule number 1. Rule number 2. The problem comes in when you have a 0 in your number. Measured quantity that has uncertainty associated with it in the last digit. If you have a 0, that's where the problem comes in. Now, if that 0 is embedded between 2 non-zero digits, it's significant. So the example I have is the next one on here. And it looks like this. So the way I think of it is, according to rule number 1, I'm going to do the digit here, and I'm going to do that 3. And according to rule number 2 now, I'm going to go ahead and snag those zeros. Okay, what? So 5? So you get 5 sig figs there. It's all about the zeros. We have a few other things that zeros might be. So rule number 3 looks like this. A trailing 0 after the decimal place is significant. The example I have here looks like this. Okay, so the 2 and the 5 are rule number 1. And this 0 right here is a trailing 0 after the decimal. That totally is significant. So that gives us 3. The way I look at it, and this is true, this isn't just me, is a few things. Somebody cared enough to put that trailing 0 after the decimal. And do you see where this is like plus or minus 0.01 grams or whatever, versus 2.5 is plus or minus 0.1. Okay, this up here is a better scale. Okay, it's got uncertainty out to the hundredths, not the tenths. Okay, so they're 2 different things, 3 sig figs. Now, we have this deal with a 0. Well, what if you have a 0 that's what we call a leading 0? A leading 0, sometimes I call them placeholders. Placeholders. they are not significant. And you'd be like, well, it tells a different, it's just they aren't. And I'll try to show you maybe later why they aren't. Okay. An example, oh, this one, nope, this is an example. Check this one out. What do you think? So this is still with like rule number 3. Those first 3 digits are significant, and these zeros are trailing zeros after the decimal. So you're up to 5 sig figs. This next one now does the whole placeholder thing. So you can kind of see how I've done it. I kind of go back to rule number 1. The non-zero digits, we have a 2 and a 3. And can you see where actually these 3 digits are just placeholder, or excuse me, 3 zeros. These 3 zeros are placeholders. So I'm actually going to put an X over those 3 because they are not significant. So trailing zeros after the decimal are significant. And what did I call these? Leading, those are called leading zeros. So they're like after the decimal, but before the non-zero digits. Now, a lot of times students will ask me this. They'll be like, all right, Mrs. Snipes, what if I put the number, what if I change this 0 to a 4? So instead of 0.00023, I have 4.00023. So what do you think? Are those zeros significant now? Yes, they totally are. You got it. So then you'll be up to what? 6 significant figures? Okay. Let's see. Now, we have one more type of 0. And it is, these are trailing zeros, but they're not trailing zeros after a decimal. They are trailing zeros of a big number before a decimal that is implied. Are you like serious? I'll show you what that looks like. So for instance, oops, something like this. So if we have 32,000, you might be like 32,000, I bet it's like 32,000 trees or something like that, 32,000 people. So it's like, not necessarily. It could be 32,000 feet, 32,000 miles, 32,000 kilograms, okay? And in those cases, I'm gonna put a question mark right there. Oops. If I put a question mark right there, okay, I'm gonna keep the 2, sorry, I'm gonna keep the 3 and the 2 for sure. But if I put a question mark right there, that means that these zeros are not significant. They are the last type. They are the last. They are what I say, they are trailing zeros before an implied, the word implied means that it's not there for sure, an implied decimal. Usually if I were to ask students if this is the number 32,000 feet or whatever, I'd ask them where the decimal is, and they would probably say right here. Okay? Implied, and when I do it, I'll probably put a little dash around it. Meaning, it's implied, it's there, but no one hardcore put it there. Okay? So we don't know if the uncertainty starts here in the thousands place, or does the uncertainty start here in the 100s place, or the tens place, or the ones place. Notice I have here that we have 2 significant figures if this is the case. If the uncertainty starts here, we have 3 significant figures. Uncertainty starts here, we have 4. Uncertainty starts here, we have 5. So that's kind of how that whole thing works. One of my last, or slide coming up soon, says if there is no decimal, you start from left to right and you count your significant figures and assume that those trailing zeros before an implied decimal are not significant. So you're conservative is the word. Okay. It's becoming somewhat of an accepted convention that the decimal place is shown. Okay. Now, if someone hardcore put that in, all right, 32,000. If someone, and I'm going to go ahead and say, I don't have any dots around it, so someone actually put it in there. That means that the uncertainty begins here, and you're looking at plus or minus 1. So by golly, that one counts, this one counts, these two count, and everything in between counts. So you're up to 5 sig figs. Yep. 5 sig figs. Now I'm going to show you, because you might run into this. You might be like, well, I have 32,000 on each report, and I'll try to show you how you round here in a minute. But I need to round, and I need to show 3 sig figs. So what am I gonna do? If I leave it without the decimal, it's 2 sig figs. If I put the decimal, I got 5. How do I get 3? And the answer is to ball it up into scientific notation. Now, I'm not gonna, in here I'm assuming that you've had math. I know you've had math. But that you understand scientific notation. So, kind of with that in mind. Okay. So, with scientific notation, I said I was going to talk about, but just briefly, just to kind of get you remembering how this whole thing works. In astronomy, scientific notation, we just carry about big numbers, okay? In chemistry, we need big numbers to pack them up and unpack them, and we also need small numbers. So you might remember that, and we'll just take the example of 32,000. Really? Okay. So 32,000. Okay, and the implied decimal is right here. All right. So to pack things up in scientific notation, we have a coefficient part. And actually the word coefficient, as some of you guys maybe know, in chemistry has 2 things. It has this with scientific notation. It also has to do with balancing equations. So we have a coefficient part times 10 raised to a power. And this is the exponent part. Okay, the coefficient part needs to be, I usually just say between 1 and 10. I know there's like splitting hairs sometimes, but between 1 and 10. The exponent part, if we are packing up a large number like this and moving the decimal, like get my rights and lefts mixed up, moving the decimal from the right back to the left, this is going to be positive. Positive for large numbers. And here in a minute, we'll do an example of a small number, and we're going to move the decimal for a small number from the left to the right, and then this exponent, or power of 10, is going to be negative. I'm not a math teacher. Negative for small numbers. Okay. So here we go. We're going to move this 1, 2, 3. We're going to move it 4 places, so we get a number between 1 and 10. Okay, so right off the bat, since I moved it 4 places and it's a large number, I'm going to make that 4. And then my decimal number is 3.2. 3.2 times 10 raised to the 4th power. Now, here I tell you, you count sig figs in the coefficient. So right off the bat, I'm just telling you that if you had, you need to show, well, let's put it this way. In my coefficient, how many sig figs do I have there now? 2, yeah. How do I get 3 sig figs? Try to trailing 0, exactly. So here we go, 2 sig figs. If I need to show 3 sig figs, 3.20 times 10 to the 4th. Notice that, and this is one of those things where I know when I was looking at the slide, sometimes I'm like, they're the same number? Yes. Well, kind of. They have the same value, but they're relaying. This is a better measuring equipment in a sense. Okay? 4 sig figs, I put another trailing 0 after the decimal in the coefficient. And this is my favorite one, 5 sig figs. You're like, are you serious? Well, based upon what I just told you, why not just put 32,000 in a hardcore decimal? Okay, it's the same thing. Are there any questions about this? You don't want to be doing all that. Okay. Some people use the convention that when a number is represented in measured quantity is written ambiguously, that's kind of like the large number, the 32,000, it's assumed that it represents the fewest number of significant figures. So this is consistent with when I said 32,000 with no decimal, 2 sig figs. Okay, that's kind of what I said a minute ago. Okay, we're gonna finish this whole part. Ready or not? I couldn't stall anymore. This is very important. That's why I was like, oh, we should just wait. No, we should go ahead. This actually sets the stage for working all calculations in this class. Let me tell you about the rounding thing, just to kind of put the spin on it. There are different ways you can lose points in this class with your homework, or especially on the test. I don't look at your homework too much, but I really do look at the test, okay? On your test, you lose points if you don't round correctly. And this is what I'm going to kind of tell you. And sometimes students will say, Mrs. Snipes, how do you want me to round it? I'm like, no, it's not how I want you to round it. It's how you should round it. Okay, so let's see how that works. It's broken up into 2 types of mathematical operations in general. Okay, and I think we're going to start with adding and subtracting, and then we're going to go on to multiplication and division. Okay, so it makes a difference how you round based upon your mathematical operation. So here's the deal. We're starting with addition and subtraction. This says, if you read it a few times, basically I will paraphrase, that you round according to the fewest decimals. And if you don't have any decimals, it's the fewest tens places. The word conservative actually would work for both of these. So you are conservative one way or the other. Conservative. Okay? And with adding and subtracting, it's, you know, it's not that complicated. Fewest decimals, or if it's a large number, fewest tens places. Now, one of the things about adding and subtracting is, you know, you could have a list of, you know, like 20 things you're going to add and subtract, right? All you got to do is after you add and subtract them, you take out your calculator, and whatever your calculator says, you round to the one that you have the fewest decimals. That's it. So you do your calculating normal. It's just how you round it. A lot of times I'll tell students what I do sometimes is in my answer keys, you'll see a C-A-L-K, like C-A-L-C, excuse me. Maybe that's German. C-A-L-C for calculator, and then you'll see the rounded one. Because I'm like, hey, I love all my digits. But then I'll be like, oh, but I can only justify so many. So I'll kind of show you why that is. All right, so for instance, if we have these 2 volumes, and one was fancier than the other, okay? In the first, we have like plus or minus 0.001 is how well we could read it. And the other one's plus or minus 0.1. We're going to add those volumes. That happens all the time. Based upon what I just told you, do you see where the first number we're adding has what? 3 decimals. Now again, if all out sig figs, you're like, oh, you just sig figs. Well, it's coming. But with adding and subtracting, it's decimals. 3 decimals and 1 decimal. So how are we going to round it? Our choices are 3 or 1. We're always conservative. How many people are going to round to 3 sig figs? 3 decimals. How many people think of 1 decimal? Is 1 decimal. Yep. And I'll kind of show you how that works. This is the behind the scenes sort of thing. Again, the red number is uncertain, right? Red hot, red hot. We line them up on the decimal, bring them down. And do you see how what we say, I love this term, the uncertainty propagated through the addition problem. So the uncertainty propagated through. So basically we have uncertainty here in the tenths due to our 26.4. Of course, we have uncertainty in the 0.001, the thousandths, according to the first one. But everything in between is uncertain. So I said, just based upon just eyeballing it, and not all this stuff behind the scenes, you guys told me 1 decimal. 1 decimal is right. I just kind of showed you how it propagated through. One of the things you probably learned before you got here was if I need to round to the tenths, what I do up here then is I am going to truncate it here, and so I look at the next digit, and since it's a 4, I keep it the same. And I think the rule in here we go, if it's a 5 or above, we round up. Okay, you good with that? So I think for your homework, you're going to have some fun with that. Okay. And anytime now in here, I'm going to be looking for that. Okay, that includes your, I don't look much at your homework, like I said, I will a little bit, but I'll really be looking for things like this in your exams and things like this in your lab write-ups. The next one is the multiplication and division. And honestly, we do a lot more of this. If you guys remember in your other chemistry days, we do a lot of we do a lot of multiplication and division, not much adding and subtracting as much. So it changes. Now we get to use those skills that we just did, okay? Now again, it's conservative, but it's fewest sig figs, significant figures, significant digits. All right, and I'll kind of show you why that is. So we're going to knock out the area. We don't do much with area in this class. We do more with volume, but in this case, we're just going to knock out the area of a rectangle. And of course, if you have the two dimensions, unique dimensions, you multiply them by each other to get the area, and that's what we're going to do. So again, we've got two different length measuring devices, 12.34 centimeters and 1.1 centimeters. So we're going to multiply those two together. Just based upon this rule over here, okay, let's see. How many sig figs in 12.34? Use your fingers. I'm liking it. Very good. 12.34. How many sig figs in 1.1? 2. So what's the fewest number of sig figs? 2. That's it. I'm going to show you how it propagates through, but that's it. That's all. We don't have anything more complicated than it is. When I say 2 sig figs, you're going to start at the left and go to the right, picking off 2 sig figs. That's it. Whatever that third digit is, you're going to see if you have to round up or leave it the same. All right, here we go. Here's how the uncertainty propagates through. So old-timey, how we learn how you multiply things is you line them up, and then you multiply. This is so confusing. I think what you're going to see here in a minute is I'm going to take this 1, and I'm going to multiply through it here. Now, since that 1 is red, anything it touches turns red. Okay? And then I'm going to move it over a column, and I'm going to take this number in the 1's place, and I multiply it through, and then I'm going to add those together. This is long multiplication. And then I'm going to line them up, I'm going to add them up, and then I'm going to count the decimals. I have 3 decimals up here, and so I'm going to put the decimal 3 decimals in. So that's long. I don't know if you guys still teach that anymore, because we all have calculators. So here's what it looks like. Taking this digit right here, 0.1 times 12.34, I get 0.234. It's red hot because my 0.1 is uncertain. Then I have to move it over and take that same quantity times this. Of course, I get 1, 2, 3, 4, and my 4 is contaminated or red hot because it was uncertain here. And then I bring them on down, okay, and I get 1, 3, 5, 7, 4. And longhand multiplication, I go ahead and go 3 decimals in. Okay, there we go. Now, based upon kind of seeing how the uncertainty lied, we actually see it turn red hot here in what ended up being the 1's place. And based upon what I told you earlier, we can only keep 1 red hot, 1 uncertain number, so we're going to have to truncate it here. And the rules are, what do the rules go when I say since this is a 5, are we going to leave this a 3? Or how many people think we're going to round this 3 up to a 4? Me too. Yep. Okay. Now, this is a good example, like I said a minute ago, of you'll see me write, above it, I'll write CALC, because I want the world to know that's what my calculator spit out. But here, I will probably write like ANS, for that's the real correct answer. It is a form of line. 13.574 centimeters squared is lying. I mean, I'm not going to turn it in for plagiarism or whatever, but it's not there. 14 is correct. Okay, fewest sig figs, multiplying and dividing. So this just kind of recaps the key to report an answer obtained by adding or subtracting. We said was decimal places. If there's no decimal places, then you have to go with digits like tens. Ask me if you have any questions about that. But if you're multiplying or dividing, then you have to count and be conservative again with regard to sig figs. If in your calculation somewhere, like if you're multiplying like 10 numbers, and if one of those 10 numbers is an exact number because it's counted, or exact number because it's by definition, that you don't count that as introducing any uncertainty. So you don't count that when you're trying to, if you're multiplying or dividing, count sig figs. Okay? Sorry guys. You got 2 parts today. I don't think I talked too fast. I record myself. If I talk too fast, let me know. But so you have 2 parts that are due on Wednesday. Okay? Let me know if you have any questions, but we're not going on to the next part. That's just ridiculous. That gives me a minute to go get a syllabus.